My name is Suman Karumuri. I am currently working on PinTrace. That's what I'm going to talk about. It's the distributed tracing pipeline for PinTrace. So a little bit about me before we start. I'm passionate about distributed tracing, monitoring, and cloud infra in general. Currently, I'm working at PinTrace. I'm the lead on the visibility team. Previously, before this, I was at Twitter. I was the lead for Zipkin project over there, briefly. And currently, I'm authoring a book on distributed tracing for O'Reilly. So motivation. So why did we do distributed tracing? So I'm going to take you through a gradual step-by-step process of how we decided to do it, just in case you're in one of those steps and you can maybe say, hey, like we're going to go through these steps anyways, so let's just go all the way to the end, right? So why do we care about distributed tracing, right? Pinterest is a social media company. I hope you know by that. We care about getting users hooked. And the key to getting users engaged is speed. And we have seen over and over again how speed improves engagement among our users. And we pride ourselves in providing a fast, reliable service for our customers. And just like any other company, to handle the scale and services, we also have a microservices architecture. But the problem is our tools are broken in the microservices world. So we don't have any tools to understand the latency of a request. Let's say a home feed request was done. It runs across 40 services or 50 services, and you have no idea if it's slow, which one of those services is slow, right? It can be any of those services that can be slow, that can cause the overall request to be slow. And microservices broke our tool. So what do we do? So just like everyone else, we started with metrics, right? Metrics are you aggregate events across your service, and you put them in dashboards, and then you see trends, and then you can alert on those trends, which is awesome. They're also like basic atomic counters in your code, so they're pretty cheap to implement, pretty fast to add and update. So people tend to use them, and they're really great. However, they only provide you a host level or a service level overview. They are not request scope. They won't tell you if a request called 10 other services, which request was, like it'll tell you, hey, like this request took 10 milliseconds, this request took 8 milliseconds, but it does not tell you, hey, this request is related to this request. That information is not there in a metric, right? So you can't use metrics to understand the latency of an application. So what do we do, right? We generally use logs, right? What are logs? They are very flexible. You can log whatever you want, right? And they are discrete events, so you can log wherever you want. And then you aggregate these logs into a single log set service where you can search by request ID or one such parameter, and you would see all the events that happened on these logs, right? Which is great. But there are a couple of problems. The problem is you have to manually correlate how the request is executed. If you're searching by time, time is broken on all these machines, right? Like the time on one host won't correspond to time on other hosts. So if you're searching by time, you may find it, you may not find it, right? And the other problem with logs is while they are flexible, they are more expensive than metrics. Not only that, they're also very brittle. For example, you are relying on an application developer to add those logs and log the necessary request ID and things like that. So potentially, your logging can break every time there is a deploy, because the developer can make a code change and then not log the request ID or not log the request at all. And then you cannot track the request across your services. And if it happens somewhere in the middle, if you drop this request ID somewhere in the middle, all the services which are downstream won't even know about it. So this is why understanding how a request is processed from logs tends to be very brittle, and it's not reliable at all in practice. So what do we do, right? So the next step we did was actually manual tracing. What is manual tracing? We basically took our logs, we took our metrics, and then we took a bunch of very senior engineers in the company, and then we gave them the code and asked them, hey, find out why it's slow, right? And we named it Project Prestige, just to make it sound like a good thing. And we did find optimizations that way, right? We spent 2 quarters of the company's time, of the most senior engineers across the company, looking through all the paths along the search path, and we did identify 50% latency optimization. We cut down the latency, search latency in half, right? And they didn't really do anything crazy. They just realized that we are calling the spam service and a couple of other services that were not needed, and they just decided we shouldn't call them, and then search latency dropped, right? So, but there are 2 problems with this approach. The first problem is this approach is like that guy skating down the mountain, right? It's dangerous. You cannot, like, once you did it, it's not repeatable. Like, you have to do the same thing again, and you need a lot of skill, because you just can't have any developer just looking at a trace and like understanding you shouldn't be calling these things, or this is what is happening, right? And then we were like, okay, so this is good. So we built this tool called Pinpoint, right? What is Pinpoint is, Pinpoint just does request correlation in a single service, right? The problem with Pinpoint was it used network level socket information to do the request correlation, and it only worked in single service. It was promising, but it didn't give the answers we wanted. So we said, okay, let's just do full-on distributed tracing, right? But what does that mean, right? Like, I mean, people say distributed tracing, but what does that mean? Distributed tracing is nothing but you record events that are happening on a request in causal order. Causal basically means in pretty much like the time-ordered fashion, in the order they happened, right? So let's take a very simple example. Let's say you have a client, and let's say you have service 1 and service 2. So the client talks to service 1, and service 1 in turn talks to service 2 to get some data. And then once service 1 gets a response, it does some post-processing on that, and then sends a final response to client, right? So in this transaction, right, let's see the events that are there. Let's call our request R1, right? So at T1, time T1, so we are starting at the top here. At time T1, the client sends a request, right? And at time T2, the server receives the request. At time T3, the service 1 sends the request to service 2. And at time T4, the server received that request, right? And at time T5, the service 2 sends a response to service 1. At time T6, the service 1 gets the response from service 2. At timestamp 7, the service 1 is done processing the request. It sends a final response to the client, and then at T8, the client received the response, right? So these are a record of events. So what distributed tracing is basically we capture these events into what is called a span, and then we make those spans into a graph, and we call that a trace. That's all distributed tracing is, right? So here, a span is nothing but any logical operation you can think of. Here, we are saying that a request and a response pair is a span. So if you like look at the screen, all the red events belong to one span, and all the green events belong to one span, right? And because spans need to have an identity, we gave them names S1 and S2. And to represent that parent-child relationship, the fact that, hey, like service 1 made a call to service 2, we make S1 and S2 as a parent-child relationship. And this essentially is a trace. And when we are doing distributed tracing, what we're essentially doing is we are constructing traces across our services. So in some sense, distributed tracing is just structured logging on steroids. You're just doing structured logging, but with some fancy data, right? So what is PinTrace? PinTrace is nothing but the same exact idea applied to all of Pinterest infrastructure, where we trace a request all the way from mobile clients like iOS, Android, or web clients, all the way to our backend databases like HBase, MySQL, or Memcache, whatever the data stores are. The PinTrace project is basically tracking that request all the way through. So what did we do? We basically took Zipkin-based open source components and then built a tracing pipeline, right? And if you were paying attention, this tracing is actually more expensive than the metrics and logs we have seen. The reason being, we are capturing more data, and we are tracking the causal relationships between that data, which means we are doing more work, so it's more expensive. We'll come back to how we'll reduce that expense here in a bit, right? So so that's how we decided to build PinTrace, right? And when building PinTrace at any company in a heterogeneous environment, you'll have a ton of challenges. So I'm going to talk a little bit about the challenges we faced when we were building this component, right? I mean, you probably have seen like Zipkin talks or like open tracing talks or some tracing framework talks where people come in, show you a demo, and you're like, hey, like I just add this API and it's done, right? But this is what happens after you see the demo and you go to your home and you try to do, like go to your company and try to do it. So these are the 5 challenges we faced, and I think these are general enough that you'll probably see them too. So the first challenge is building instrumentation. So building instrumentation tends to be very hard and tedious, right? Like if the reason it's hard is because generally adding instrumentation is really easy. Like adding instrumentation is pretty much like adding a log message. But the problem is you need to add the log message in the right place in the code, and generally that's the code any developer generally doesn't look at. It tends to be somewhere very core to the framework, and it's generally abstracted away from the developer, and you just take that for granted. So you have to add instrumentation at that part of the code. So that is why if your framework already comes with instrumented code, it's a really good idea to use it. Then you don't have to worry about it. You just use it, right? The reason you have to do instrumentation whenever you adopt distributed tracing is, as developers, we like to build things and we like to make everything custom. So every company has their own custom web framework. So whatever you see in open source, it needs some adaptation generally to build that instrumentation. So that's the hard part. The tedious part actually comes because you're not just building instrumentation once. You're actually building instrumentation for a language, framework, thread pool protocol combination. Let me explain what that means. So you're building instrumentation, let's say you use Python with Flask, right? And it has its own like event model and a threading model. You build instrumentation for that. And if your request processing is over HTTP, you have to take the request ID from a HTTP protocol, or you have to, if it's Thrift, you have to extract it from Thrift. So that's 2 protocols you need to deal with. And the third thing is, if you have a Flask app talking to Memcache, you need to also instrument the Memcache protocol. If it's MySQL, you have to instrument MySQL. So you have to build pretty much tracing across all these protocols and thread pools and things like that. And if you're Java, you have to repeat the same process again. If you're Python and Django, yeah, again, do the same thing. If you're doing it for Go, do the same thing. C++, same thing. So the problem is you have to repeat the process, and that's pretty tedious. And this is why instrumentation tends to be hard and challenging. But luckily, when we started doing it, we use, for our Java services, this Twitter library called Finnegal. And Finnegal comes with built-in tracing for HTTP, Memcache, MySQL over Thrift, and it all does the request propagation, everything pretty elegantly. So we just use that. And we had to build a tracer for our Python infrastructure. So we built a tracer based on our open tracing, based on the open tracing API. We built a tracer that basically tracks a request across our Python framework. Our Python framework is pretty custom, so it's pretty hard to do it, and it's also pretty hard to get it right. But finally we did it. So once the hard part of instrumentation is done, next comes, now we have a tracer that is tracing a request that is generating events and generating those, aggregating those events into a span and like logging a span, right? Now, what do you do with those spans? You need to aggregate those spans and like you need to store them somewhere. So you need to build a span aggregation pipeline. This is the next challenge you would face. So you have to aggregate the spans. Generally, on a small scale, you would just like write these spans out by doing a HTTP call to a backend or something like that. But in any large company where you're dealing with tens and thousands of nodes, you want to generally use a store and forward mechanism. So what we do is we take the spans, write them to a file, and then we have this tool called Singer, which reads the spans from the file and then writes them to Kafka. So, and that's what we do. So the Singer pattern was actually a very well-known pattern across the company. But the challenge when we were doing this was, it was the first time we were doing Singer across the company, and that posed like a few challenges. The first challenge was there are like 30,000 hosts writing to Kafka, and then there is too much load. And the other thing was, if you're deploying across every host in the company, you have to deal with permissions, security issues. Those teams don't want you to mess with their things, and all sorts of things. So setting up the aggregation pipeline across the company was hard for us. But if you have something like that in your company already, it should be pretty easy. You just like copy paste that stuff and it should work. The third challenge we faced was deploying this instrumentation. So deploying instrumentation basically is you have built this tracer, you have built this span aggregation pipeline. Now you need to tell the service owners that, hey, like I've added this to your application, now go deploy it, right? Should be simple, but no. It was also pretty challenging for us because we were trying to target about 100+ services to deploy this to. And we did 3 instrumentations roughly, deployed it to 100+ services, but we had to talk to roughly 40 teams within the company just to get it deployed. And it was actually pretty hard to get them to do it because in some cases, there were services which were doing really little work, like look up a number in a cache and return it, right? It's like a very fast operation. But what happens is my tracer is generating events which are like an order of magnitude larger than the single number they're returning, right? And they hated that. They had to like tune their memory and things like that. So we had to work with all those teams, allay their fears, and like, hey, tell them, hey, like this is good for the company, and if we do it, it'll be beneficial for you too, and things like that. And finally, they did it. But before that, we had to do one thing. So remember, I told you tracing was expensive. We had to strike that balance where the traces that we were collecting were useful, while at the same time, they were not causing any performance issues. So the nice balance we found was somewhere between 0.5 and like 1% of the traffic. Once we do that, it looks like the traces we collected were valuable, and at the same time, the performance overhead was negligible. So that was the challenge with deploying it. This is mostly like PM work because you need to like just talk to people and ask them, hey, did you deploy it? Did you deploy it? Did you deploy it? Yeah, and finally, yeah, oh, the other thing. Anytime there is an issue with their deployment, because they're not just deploying your code, they're deploying their code too, the first thing they'll do is blame you. So yeah, that's the other thing you need to deal with. So finally, once the code is deployed and all the traces and the requests are traced and the spans are flowing into a pipeline, you need to like aggregate them into traces, right? So what do? You take those spans that are coming off the Kafka pipeline, and then you store them in ES, right? That's the standard Zipkin pattern. So when we started doing that, we saw 2 problems. First problem was the Zipkin backend at the time did not scale for our volume. So we had challenges there. The second challenge we had was that the spans that were being generated, although they were mostly right, there was a small problem, which is some of the instrumentation from Finnegal, because we use a really older version, had bugs in it. So we had to fix those spans up when we were ingesting. Both of those we couldn't do with the open source Zipkin stuff. So what we did is we created a Spark job that would take all the spans and then construct traces, fix them up in the process, and then write them to ES. And the other reason we did this is, remember we were doing 1% sampling? At some point in time in future, what we wanted to do was we wanted to sample at a much higher rate, but process all those traces in the Spark job where we can just drop them and only drop the common ones and only keep the outliers. So we also wanted to do that. So for those two reasons, we decided to go with the Spark job approach. And we did the Spark job, we deployed it to production, and we were talking to Adrian Cole from Zipkin, and he was like, hey, like this is cool, so we contributed our code to the Zipkin community. You can access that code under Zipkin Spark Streaming today in GitHub under the Open Zipkin project. And once we have the traces in ES, right, we need to tell our users to use it. So we have to stick a UI in there. So we just took the stock Zipkin UI and then configured it to just talk to our ES backend. And now you can search for traces, and then you can look for them in the UI, right? And this was back in May sometime, so there was like the talk about the wall. So we also had a project called the wall internally, which was supposed to give a company-wide overview of all the key metrics and things like that. So the wall project also pulled the Zipkin data to build a service dependency graph and show it on the Zipkin UI. So we did that, and sorry. OK, so and finally, we have our traces in the Zipkin UI, right? And here is the realization we had, which is like once you set up tracing, right, you would think that, hey, like now I have traces, now I can solve all the problems I want, right? Actually, that's also not true. Traces are data, right? So we are giving you raw data, and it's up to the developers to like understand how to use them in their day-to-day activities. So this was another realization we had. So let me talk about how we actually use this trace data to understand, debug, and tune our applications. I'll just give you like a few things that I can just explain in a talk that are very short. But we have written a blog post about it in detail, and you can go read it, which has more information, right? So let's see the first application. So one of the biggest things in our architecture was like we have like big O of 100 microservices, and we get like millions of requests a second. So one of the first questions we ask is like, nobody understands what the hell is happening. So the first thing we wanted to see was, OK, so what is happening with the request, right? So we wanted to understand what services are interacting with this request. So we look at a single trace, and you'll be surprised how much data you can obtain just from a single trace, right? So this talk is about how much data you can obtain from a single trace. There are things you can do with aggregated traces, but I don't want to focus on that for this talk. So just for a single trace, if you go to a Zipkin UI, like the one we saw before, right? So you'll search for your traces in the UI, and then it'll show you a list of traces. You click on a trace, right? The first thing you'll see on a trace is this trace header, right? This trace header is nothing but a summary of that trace, right? So what is it showing? It shows you a few things, right? It shows you the duration, which basically means that how long this request took. So in this case, this request took 581 milliseconds to run, right? And it shows service count, which basically is the number of services this request interacted with. In this specific case, it interacted with 38 services. But in practice, we found that a request interacts anywhere from 24 to 48 services in our backend. And it shows that the depth of the trace is 1, which basically means that if I call a service, that service is in turn calling at most one more service, and that's it. That's our depth, right? And the number of spans is 97, which tells me that because we are mostly tracking network calls, this basically means that I made 97 network calls to serve this customer, right? And it also shows you a summary view of the services in this request, right? So you can see that it's a little harder to see, but you would see on the second line there, you would see graph service, right? Graph service, and you'll see a small x and 20. And what it says basically is that there are 20 calls made to graph service, right? And just beside that, you'll see graph service client 17, which means that 17 of those calls are made by graph service client. And until this point, we did not know that there were other graph service clients that were Java. So this is, just by looking at this data, like you can glean insights like this, right? Which were not possible before, for us at least. Then the next thing is identify duplicate computation, right? So anytime you look at a trace and you see spans that are duplicated, right? They have the same name and they are close to each other. That's a pattern. What it means is it is a sign, possible sign of duplicate computation. So what does duplicate computation mean? It's basically making the same call twice, right? So when we noticed this in our traces, we actually went back to the code and looked through it. And what we saw was there is a class with a couple of methods. And at least the documentation-wise, you were supposed to initialize the class that will get all the data, and then you just like do local lookups. But at some point, somebody went in and added a method that actually made the network call again. And then the users who were using it didn't know about it. So every time you make a class, create this class, and then call a method, you were making 2 network calls, right? And what did we do? We just went in the code and then removed the additional network call that was not required. And suddenly, we did not make this additional network call, which dropped the load on the downstream service by half, because this is like being made for every home feed request. So we saved like half the capacity. And at the same time, we improved our latency 5%, because this was like computation that is serial and we didn't need to do it. So this is the other win we had. These are wins that we had right away. So the other thing I want to talk about is, so that is like, the previous ones were like, understand what is happening, right? A couple more examples about how you can use it to debug. And this is kind of to understand what is happening, but this is in a different context. So let's say in our home feed request, we have about order of tens of Memcache clusters and high number of MySQL clusters, right? And a given home feed request can hit any of these clusters. And previously, it was this big challenge when SRE would ask, hey, like, which cluster is this request hitting, right? You had to like talk to core services, and then they would talk to HBase team, and then the HBase team would tell you, oh, this is the cluster, and then again, that message would like come back up all the stack, right? Like, it's very inefficient. So what we did was we added instrumentation into the trace to show which cluster the request is hitting, and also we showed which query it was. And once we added this, like SRE would just go look at the request, and then he would know which cluster it is hitting. So this is an example span you see here. So it's doing a MySQL read. It's hitting, this is an example of a Zipkin server, but we had the internal stuff. I didn't bring it, but here you're hitting the internal server address, and it shows you a sample MySQL query. Our internal thing looks pretty much the same. So this is great, right? So the second thing, once we were starting looking at traces, we realized was, when we were reading the traces, one of the things was the spans didn't map to the developer's mental model, right? So the spans are like network calls, but developers don't think like that. They think in the sense that, hey, I'm making a call to for authorization. Then I'm making another call to actually handle the call, right? And then I'm making a call to these services. And when we look at our traces, this aspect is not coming through. So what we did was we gave the developers, our developers, the ability to add custom spans to a trace. So what is a custom span? So if you look at the trace here, the second span here, it starts with fn_auth, right? So it's a span that they added, which basically shows all the calls that were made during authorization. So that's a custom span. Anything starts with an fn in our traces is a custom span. So here, developers added fn_auth and then fn_v3 handler to actually document their domain knowledge of how they think about the traces. So SRE or a developer looking at this will say, hey, like all the calls between fn_auth and fn_v3 handler are related to authorization, so I don't care about them. Anything after v3 handler are related to my code, so I'm going to care about it, right? So, and when an SRE is looking at it, it's pretty easy. They know kind of like which request is processing this, or at least like which team to talk to by looking at this. Then this is like just a tiny thing, which is identifying clock skew. If you have a cluster of tens of thousands of nodes, clock skew is like a fact of life. So we kind of try to identify clock skew using various means. One of the ways we expose the clock skew to our developers is when you see a trace, you would see some of the spans that happen after this request happen before. And whenever you see that, that's a sign of clock skew. So in this case, you would see that user service was the user is another service. It should be called after the user service, but if you see the timeline, it's actually called before. And the reason that happens is because there is clock skew between those machines. So that's one way to identify clock skew. That's to debug issues, right? So I have one more example of how we talk about identifying serial execution. So when we're looking through our traces, whenever you're looking through your traces, you see a step pattern. That's an example of serial execution. And as we all know, serial execution is bad. But actually, the answer is it depends on the context, right? So serial execution can be the process is inherently serial. It can be because of that. Or it is because of a bug in your code where it can actually be parallelized. So in this specific case, we were making memcache calls, all of which are supposed to be parallel, but then the memcache get many call, was not being executed. It was executed serially, as you can see in the first image. You see a step pattern, right? So when we went back to our code, we were looking at why this was happening, and what we realized was we had a memcache client, and it had multiple calls, and each of those calls had a decorator annotating a decorator that wrapped the call in an asynchronous call. But when some developer forgot to annotate the getMany call, so that call was being executed serially. So we went in, added the annotation back, and then when we launched it into production, all the getMany calls now became parallel, which you can see in the second image. So there are more applications of this trace data that we see in practice. For example, if you have a very bad P99 latency, you can track that down using traces. It won't be real time, but if you look at long enough periods of time, you hopefully capture one of the P99 requests. We actually use this in production. We have a service called follower service, which gives a list of followers to the users. Generally, it takes under like 30 milliseconds, but sometimes we see some things that took like a second, right? And we use the trace to identify why that is, and we realized that the client was calling the service with, generally it would call it order of 10 IDs. It was calling with like thousands of IDs, and when that happened, this service was taking a long time. And once we knew this was happening, they just went in and limited the number of IDs you could return, and things were back to normal. So the other application in production we found are identifying architectural optimizations. Generally, these are really hard to do. So here are a few things we observed from the trace I showed you earlier. First thing we noticed is we were making the call to render the ads somewhere between like 100 to 200 milliseconds after we get the request. But ads takes another 500, 600 milliseconds to execute, which means if we move the ads, if we start the process call to ads much earlier, we would be saving whatever additional time that ads is lagging, because that's a straggler. And we are in the process of doing that now. And once we do that, we'll just gain an additional 100 to 200 milliseconds latency just by changing the call order of the call. And that we identified from traces. The other optimizations we found were things like every time you render a home feed, you have a service that tells you what pins to render. And then there is another set of calls that are made to fetch those pins, stitch them together, and show them to the user. We realized that 30% of our time is going into rendering those pins. And when we did that, and after tracing it, what we realized is we are looking at ways to optimize that part where we are trying to cache already formed pins so we can just render them really fast. And the other application of tracing that we saw was our client-side teams, Android and iOS teams. They also capture tracing information. Just like if you are a web developer, you would open the console and look at the network flow. Similarly, our iOS developers are also capturing those network flow diagrams. And the way they were doing it was they were creating custom span formats and custom Hadoop jobs to process that data. But we went to them and said, hey, like, you can just use a trace for this. We gave them the Open Tracing API. Now they're starting to log all their data as traces. So we can actually use the same PinTrace pipeline to actually store, process, and visualize that data. And we don't need all those like Hadoop jobs for all those data types. And we also do service dependency analysis. These are things we are like starting to do now from trace data. We are trying to improve the time to triage. Like every time there's an incident, we want to use the trace data to like tell the SRE team where it is. Because what we have noticed is every time there is an incident, like an hour or something is spent just in identifying where the problem is. And anytime we reduce, anytime we can shave off from that is time that goes towards MTTR. And finally, we are trying to do some automated root cause analysis. We are not there yet. It's a future item. And so finally, I'll just summarize the lessons learned while we built this. So one of the first things we realized with traces is user awareness and education is the most important thing to make tracing successful in your organization. The biggest reason most people don't use tracing is because, number one, they don't know that it exists, and number two, they don't know how to use it. And if you fix those two problems, tracing will be successful in your company. The second lesson we learned is begin with the end in mind. Like when you deploy a tracing infrastructure, you need to know why you're deploying a tracing infrastructure. People, like I've seen some people just do it because it's cool. But you need to do it to get an end in mind, right? You need to know what problem you're solving. Are you trying to solve a latency issue? Or are you trying to make developers' life debugging easier? Or are you trying to understand what the hell is happening, right? Because the systems you build and the decisions you make, like when you're building that pipeline up, the way you build the pipeline varies depending on the outcome you want. Like if you just want to understand what's going on, right, you can just run the tracing in test and then just like not even deploy it to production, right? Nobody cares what happens in test, right? But if you really want to like understand production failures, you want to have a higher quality of tracing, deploy to production, and things like that. So the other thing you need to do is to get most value out of trace systems is tracing infrastructure is you have to trace the most valuable paths in the application. You can say that, hey, I'm going to trace everything. That's great. But what happens is when you trace everything, it's a lot of time sink and it'll take a lot of time to show value. But if you trace only the most valuable paths, you can get value really quickly. And the other thing you need to remember is distributed tracing landscape is confusing. Hopefully, so you need to read about it a little bit. There is some documentation that's scattered a little bit over the place, and I'm hoping the book I'm writing will fix that a little bit. But that can be confusing, so watch out for that. And finally, quality of traces is more important than quantity of traces. So it does not matter how much trace data you collect. What is very important is what is in the trace data you collect. Like the quality of the trace is of utmost importance than the quantity of traces you collect most of the time. And yeah, thanks for your time. Thanks for inviting me over here. And if you have any questions, I'm available to talk afterwards.